Our project uses RRT path planning to find a path for a robot to navigate through a maze. We found this interesting because this works for an arbitrary maze, and even in the same maze, a different path is found every time. This project touches on most of the topics we've covered in this class this semester and combines them to achieve a goal. RRT is rapidly exploring random tree path planning. The RRT algorithm plans a path to a goal from a specified starting point that avoids walls and other obstacles. This algorithm first determines whether to use the goal point or a randomly generated point as its current point. It then selects a point a short distance away from the starting point or the root node in the direction of the current point. If a path can be made directly to this new point, it becomes a child node of the root node.
The algorithm then once again determines whether to move towards a goal or a random point, selecting a new current point. As the algorithm progresses, it uses the closest node to its current point as the active node rather than the root node. Like with the root node in the beginning, a new point is selected a short distance away from the active node in the direction of the current point to become the active node's child. If an obstacle obstructs the line between this new point and the active node, the new point is not added to the active node's children. A new random point is generated, and the closest node to this new current point becomes the active node. As the path develops, child nodes will have children of their own, branching out, giving them their tree nickname. Each node has only one parent, which is how we determine our final path. Once the goal has been reached, we get the parent of the node at the goal point, the parent of that parent, and so on, taking note of each point until we reach the root node.
One of the pieces of this project we developed from scratch is the code that implements the RRT algorithm we just described. This code makes use of Dr. Sprague's map reader and map utils code. It publishes the points on the RViz map every time it creates a new point. Once a path has been found, it also publishes that path on the RViz map. In order for a program to publish to any topic correctly, it must have a break in between publications. Our break was 1/10 of a second. Because we wait every time we publish a new point, our code runs the algorithm longer than it normally would execute. After a path has been found and published, our code then publishes each point along the path from the root to the goal, which causes the delay in the turtlebot's movement.
Another piece of code that we wrote is our path navigator. This subscribes to the goal topic that our RRT code publishes the points to. When a point is published on this goal topic, our path navigator adds that point to a queue. As soon as the first point has been added to the queue, our code begins to move the turtlebot towards that point by turning until the point is right in front of it and moving forward until it has reached less than a centimeter away from the point. We reused some of our code from the Turtle Sim homework and the mapping programming assignment to complete this task. Once it reaches the point, it gets the next point in the queue and moves to it, and so on until the queue is empty. Because it does not wait for the entire path to be published, this method minimizes the delay between the RRT's path completion and the turtlebot's movement.
We came across several issues while working. Some were expected, others were not. One problem that caught us off guard was mapping our maze. The maze was uniform and had very small hallways. Because of this, the turtlebot's localization code would get lost and try to fix itself, placing itself in the hallway it just moved through on the map, when it actually was in the next hallway over. After several attempts, we finally got a rough shape of our maze, which we later had to edit manually to more accurately depict our maze.
Another issue we ran into was changing the turtlebot's base footprint in the map coordinate frame. We were unable to successfully tell the robot where it was starting, so we worked around this by placing the turtlebot at the origin of the maze and pushing it to the starting point. This is why in our video the turtlebot is facing the wall and turns around to move to the first point. Robot odometry is very sensitive though, so if the robot was even slightly off, it would crash into the wall.
Unfortunately, robots aren't perfect, which makes it very difficult to be precise when navigating to points. When turning to a point, we try to be very precise with our angle, but if the angle is not exact as the robot moves towards the point, the angle error would increase and cause the robot to stop, to turn, and fix the angle. Also, if the robot overshot its angle while moving forward, it would turn the other direction. This occasionally led to the robot shuffling forward as it was constantly changing the direction it was turning.
If we were to continue working on this project, we would want to improve the speed of the turtlebot in navigating to the points. In this run, the turtlebot took 8 minutes to reach the goal. We would also want to add a wall detection feature to keep the turtlebot from crashing into walls.
It also would have been nice to be able to find the shortest path using the points in the tree. As you saw earlier, the paths that RRT plans are not always the quickest. They tend to meander a bit, and sometimes the robot will even turn around and go back to a point that it has already passed in the maze. As you can see, the robot is finishing up its path after almost 8 minutes of traversal, stopping at about 41 points along the way.